There's a hole in the ground 500 feet deep, surrounded by skyscrapers, each one weighing 30,000 tons or more. The earth around it wants to collapse inward. Groundwater is trying to flood it, and it's still open on purpose. Somebody's about to lower a 12-story machine into it, and that machine is going to dig a tunnel out the side. How is this even possible? It's an easy thing to miss. Every skyscraper sitting on city soil is pressing down hard. That weight doesn't disappear. It pushes out sideways through the dirt in every direction. Now imagine drilling a hole next to that skyscraper. You just gave all that sideways pressure a place to go, and it will go there. This isn't a new problem. We need to rewind 3,000 years. A village in ancient Persia. There's no river, no spring, no well that goes deep enough, but there's water miles away, trapped inside a mountain. Persian engineers solved it. They invented something called a qanat, a tunnel cut by hand through the rock, sloping ever so gently downhill. Gravity pulls the water all the way to the village, but they couldn't dig a single tunnel that long. So they cheated. They dug a row of vertical shafts straight down from the surface, spaced out across miles, and dug the tunnel piece by piece between them. Stay with me. Those Persian shafts, they had the exact problem we have today. Soft ground, sand, loose silt. A hole that wants to close itself the second you stop digging. How did they keep them open? Hand-built rings of timber and stone, stacked all the way down. A lining holding back the earth, one wooden ring at a time. 3,000 years later, we still use ring linings. We just changed what the ring is made of. Fast forward to right now, 2026. There are tunnel boring machines about to launch in cities all over America. California is building a 45-mile water tunnel. Pittsburgh is digging sewer overflow tunnels under a river system. New York and New Jersey are working on the Hudson Rail crossing. Every one of these starts the same way, with a hole, a vertical hole, hundreds of feet deep, and that hole has to stay open long enough to lower in a machine the size of a building. The first trick is older than you'd guess. It's called a slurry wall. Engineers dig a narrow trench, deep, but the second they dig, they pump in a thick liquid, a clay-based goo called bentonite. And here's where it gets clever. That liquid is heavier than water, heavier than the groundwater pushing in from outside. The slurry pushes back against the earth. The soil can't collapse because something's already in there, filling the space. Once the trench is open and full of slurry, they don't backfill it with dirt. They drop a steel cage in, straight into the liquid. Then they pump concrete in, from the bottom up. The concrete is heavier than the slurry. It lifts the slurry out as it fills. What you're left with is a wall, underground, already built, before anyone's stood in the hole. Repeat that around a circle, and you've just built the sides of your launch shaft before you've dug the middle. Slurry walls handle the dirt, but there's something walls can't stop: water. Most major cities sit on top of groundwater. Manhattan's water table is sometimes only 10 feet below the surface. Cross under a river and the pressure gets worse. You can pour the most beautiful concrete wall in history, and water will still find the seam where the wall meets the bedrock. And once water gets in, it doesn't stop. You don't just lose a shaft, you can lose the block above it. So how do you stop the water? The answer the engineers came up with is honestly a little ridiculous. It's the kind of thing that sounds made up the first time you hear it. Before I get to it, real quick, if this is the kind of engineering that scratches your brain in a good way, hit subscribe. We're a small channel, a new one, and every subscriber matters more than you think. And honestly, the next part is one of my favorite things I've ever read about. Okay, here's what they do. They freeze the ground. Not metaphorically, literally. Engineers drill a ring of vertical pipes around where the shaft is going to be. Then they pump a special liquid through those pipes, calcium chloride brine, cooled to negative 30 degrees Celsius. That's negative 22 Fahrenheit, colder than the deepest part of an Antarctic winter. And they keep it circulating for weeks. And slowly, the dirt around those pipes turns into solid ice, a wall of frozen earth, hundreds of feet tall, a foot thick, sometimes more. Water can't get through ice. The frozen ring becomes 100% impermeable. Engineers can stand inside it, dig, pour concrete, lower a TBM into a shaft that's only there because the dirt around it is frozen solid. The Hudson Crossing, tunnels under rivers in Pittsburgh, a few of the biggest tunnels in the world this decade, sit inside walls that are literally made of ice. Though, if you think that's wild, wait until you see what goes inside the shaft. The launch shaft isn't just a hole. It's a specialized industrial dock. Every piece in it has a job, and every job is part of the same problem. How do you get a 12-story machine to start digging horizontally when it doesn't have anything to push off of yet? First problem. A TBM moves by pushing. Hydraulic jacks at the back of the machine extend, shoving the cutter head forward into the earth. But there's no tunnel yet. What's it pushing against? A thrust frame. A massive steel backbone bolted to the back wall of the shaft. The TBM rests its hydraulic jacks against it and pushes off of this frame with up to 12,000 tons of force. That's the weight of about 20 fully loaded jumbo jets pressing through one machine. Next problem. You have to aim the TBM, not roughly aim it, aim it. Because here's a fun thing about long tunnels. If you start 1 degree off course after a mile of digging, you're not 1 degree off, you're 50 feet off. At 3 miles, you've missed your target entirely. The TBM gets lowered onto a custom-built cradle, precision milled to match the curve of the cutter head, holding it within millimeters of perfect alignment, before a single inch of tunnel exists. Then there's a question of power. A TBM cutter head can need up to 20 megawatts. That's enough electricity to run a small town. And the machine is at the bottom of a hole about to disappear into the earth. They run an umbilical down the shaft wall. High voltage cable, hydraulic lines, water for the cutter head, a conveyor for the dirt coming out. All of it bundled, all of it trailing the machine like a tether. And none of it can afford to snap. Now everything is in place. The slurry walls, the ice ring, the thrust frame, the cradle, the umbilical. The TBM is alive. Cutter head spinning, hydraulics charged. And there's one thing left between it and the dirt it's supposed to dig. The concrete wall of the shaft itself. The one they built to keep the world from caving in. It's about to be the first thing the machine tears through. This moment has a name, the breakout. Ask any tunneling engineer what the scariest moment of a project is, and most of them will say, this one. On the other side of that wall is raw earth, saturated, pressurized, sometimes under hundreds of feet ahead. If you punch a hole through the wall with no plan, you don't get a tunnel, you get a blowout. High pressure mud and water firing into the shaft like a fire hose. The shaft floods, the machine fills with slurry. Sometimes the wall above it caves in too. Engineers install something on the wall first, a double ring seal. 2 thick rubber rings mounted on the inside face of the shaft. When the TBM pushes through, it slides through those rings like a piston through a cylinder. The seal grips the body of the machine, holds back the mud and water on the other side. Without it, the breakout drowns the shaft. With it, you just get a slow squeeze of pressure and a machine moving forward. The cutter head starts to spin, slowly at first. Tungsten carbide teeth biting at the concrete, grinding it into rubble. The hydraulic jacks extend, pushing off the thrust frame. Inch by inch, the machine moves forward, through the wall, through the seal, into the raw earth on the other side. For the first few feet, the cutter head is grinding concrete and dirt at the same time, and then just dirt. The tunnel has begun. This is the whole point. The shaft isn't the destination, it's the gateway. The expensive, complicated, frozen, walled-up gateway. You go through all of it just so you can pivot 90 degrees and start digging sideways for miles. The shaft is the doorway. The tunnel is the journey. And every TBM project on Earth needs one of these doors. California is building one right now, the Delta Conveyance, roughly $20 billion, about 45 miles of water tunnel under the Central Valley. Every mile of it starts with a vertical shaft, frozen, walled, cradled, a doorway into the dark. Pittsburgh, 3 rivers meeting in one city. Every time it rains hard, sewer overflow goes straight into the water. The fix is a network of deep tunnels underneath the rivers, diverting the overflow into treatment plants instead of into the Ohio. Every one of those tunnels starts with a shaft, underneath the city, underneath the water, underneath everything. A vertical hole that should not be open, but is. 3,000 years ago, a Persian engineer figured out that to dig a long tunnel, you start with a row of vertical shafts, lined, held open against the earth. Then you connect them underground. 3,000 years later, we still start with a vertical shaft. We still line it. We still hold it open against the earth. We just use bentonite instead of timber. And we freeze the ground instead of stacking stones. But the principle? Same principle, just bigger problems. Though we've only covered the launch, what happens after the machine breaks through? How does it steer underground for miles? How do you build a tunnel while you're still digging it? How do you get the machine back out when you're done? And what happens when one of these things gets stuck? The honest answer is the engineers figured it out, same way they always do. Not all at once, not perfectly, one problem at a time. That's the only way anything this big ever gets built. Real quick before you go, if you got something out of this video, the single best thing you can do for us is hit subscribe and drop a comment. We're a new channel, really new, and every single sub means more than I think people realize. The algorithm rewards small channels that get strong signals from their viewers. So if this is the kind of stuff you want more of, those clicks make the next video possible. And from me to you, sincerely, thank you for sitting through all of this, for caring about how the world gets built, for giving a tiny channel a few minutes of your day. It means the world to us. I'll see you in the next one.